So I'll just remind you guys where we left off last week, and then we'll jump into this week's content. It's sort of like continuing last week's lecture though, right? Because we ended last week just after we had finished covering queues. So queues were a particular kind of data structure, and I did tell you guys that we would be covering 4 different data structures, right? We would be covering arrays, queues, stacks, and linked lists. So we finished covering arrays, and you guys were already quite familiar with arrays, and we'll go through some of the logic of them even a little bit more today. Queues were new to you guys, but hopefully you saw that it's a fairly simple structure. There's only a couple of commands that you have to remember. So number 1, you must remember how to create them. Okay, and creating them is quite easy. It's just like creating any other object, right? Because we're just instantiating a class. We're creating the instance of the queue class. So we've got the queue class. We give whatever the name of our queue will be equals new queue, and you've created a queue. And I want you to take note of the structure, and you probably already have from chapter 2, because we, for example, when we were creating person, right, as a person objects, we said person, person1 equals new person. Person, person2 equals new person. When we're creating rectangle objects, we said rectangle rect1 equals new rectangle, right? And now when we're creating a queue object, it's just queue, my queue equals new queue. So yeah, that's the first thing that we must remember. We must remember that NQ is how we add to a queue. DQ is how we remove from a queue. Peek just peeks, it shows us the front of the queue without doing anything to it. It just shows us the front of the queue. And dot contains will tell us true or false whether or not something exists in a queue, right? And then the last thing to remember about queues is just really like how to visualize them. When do we use them? And queues are essentially just FIFO structures. That's an easy way to remember it. FIFO stands for first in, first out. First in, first out. Cool, I see Chico's with us now as well. Welcome. I'm just revising what we covered last week before we continue. So queues are a FIFO structure, first in, first out. Whenever we need a FIFO structure, we use a queue. The next data structure that we're going to cover is stacks, and we're going to answer the same questions, and hopefully you guys will see how if you understand queues, then it's easy to understand stacks. Likewise, if you don't understand queues yet, like if you're still feeling a little bit uncomfortable, really concentrate, because understanding stacks will give you a good understanding of queues as well. All right, guys. So let's jump into stacks. Stacks are very much like queues. It's almost just like the reverse, all right? So a queue is a first in, first out structure. A stack is a last in, first out structure. Now, can any of you guys tell me, have you heard the term stack before when it comes to computers or working on computers or playing with computers? Have any of you heard the term stack before? And where have you heard it? And don't worry if it might seem silly to you. Don't worry if it might seem silly to you for now. You haven't heard it, Taffy. Oh, that's interesting to me. Do you play games, Taffy, like video games?
Yes, I do.
You do. Which ones?
Call of Duty,
Okay,
Black Ops.
Call of Duty is an interesting. So both of those games do use stacks. Chris is saying something in the chat. So he says 64 in some games. Hey, all right. So that's interesting. Yeah. So are you talking about like Minecraft, Chris, or maybe Fortnite? I think also has some concept of stacks, like as its inventory management system. There's quite a few games, right? In Call of Duty, in particular, there's a very clear place where they use stacks. Do you want to take a guess, Taffy, maybe at where you would use a stack in Call of Duty?
Probably somewhere in the map.
In the map, perhaps. I think there's a. I'll tell you where I would expect them, and they almost certainly use a stack, and that's in the ammunition of the gun. Okay. But you'll see why it makes so much sense now, because it's almost exactly how it works in real life. So we're going to start with like a fairly obvious example of a stack. So a queue is a FIFO structure. Remember that queues are FIFO structures, first in, first out. a stack is a last in, first out structure. So the last thing in is the first thing out. So just like with queues, when we use the word queue in the real world, what we mean is a first in, first out structure, right? And so in computing, it's the same. And the same is true for stacks. When we use the word stack in the real world, it's the same as when we use it in the world of computing, okay, in computer science. It's just a LIFO structure, last in, first out structure. So for example, this picture on the right here, we might call that a pancake stack, right? Why? Because the last pancake you put on the stack is the first pancake you eat. And if we think about these other examples, like why in Minecraft, when you pick up dirt, for example, is it called a stack? Well, that's because the first piece of dirt you pick up is the bottom of your stack. And virtually, obviously, it's not like literal, but you'll see how it might look in terms of an internal representation now. But each piece of dirt you pick up, you just build up a stack. And so when the first piece of dirt you put down is the last piece of dirt you picked up. So a LIFO structure. Likewise, with ammunition in Call of Duty, there'll be like a stack of, let's say, 32 bullets, and the first bullet out is the last one in to the cartridge on like a virtual level, you can understand. Okay. Anyway, but let's see how this works for us now, and hopefully it'll make sense. But I hope already it seems pretty sensible, and hopefully you guys can already connect it to your understanding of queues in all of these games. But yeah, stacks are a very, very common thing in computer science. We use them very frequently. Okay, so I'm going to jump over here. And the first thing we want to do is create a stack, okay? And when we create a stack, what we're creating is essentially just this bar at the bottom, okay? Almost like the foundation of our stack, okay? Like the bottom of our stack, okay? And so that's what I'm going to do now. I'm going to say stack, whatever my stack is going to be called, equals new stack. And notice, so when we were creating a queue, we said queue, my queue, whatever like the name of your queue should be, equals new queue, right? That's how we created a queue. And we have to use system.collections, not system.collections.generic, okay, like that. And the stack is exactly the same. It's just stack, whatever the name of your stack will be. Does anyone have a good name for our stack? Let's go with Bob. Stack Bob equals new stack. The reason I'm calling it Bob is just so you guys understand this name, it's just you make up, okay? Just like with any of the other objects, you can call it whatever you want. C# doesn't care about the name. It's just for your benefit, okay? So we've got a stack called Bob. Now, what all this is doing is in C#, it's creating this little foundation that we have here, okay? That little foundation, right? But obviously, it's not useful having just a space for a stack. We want to be able to use it. And so likewise with queues, when we had these few commands, right? We had enqueue to add to the queue, dequeue to remove from the queue, peek to look at what is at the front of the queue, and contains to see if something is in the queue. Likewise with stacks, we will have a similar 4 commands, okay? You'll notice, in fact, some of them are identical, but 2 of them will be different. So let's see, how do we add from a stack? How do we remove from the stack? How do we look at what's at the top of the stack? And how do we see what's in the stack, okay? First things first is the name of the stack dot push, okay? The command push. Push is exactly like enqueue. Push is how we add to a stack. So for example, if I say the name of my stack, so Bob dot push pancake 1, that's going to add pancake 1 to the stack. If I say dot push pancake 2, that's going to add pancake 2 to the stack. If I say dot push pancake 3, that's going to add pancake 3 to the stack. Okay, so that's the first thing. That's how we add to a stack. Quite simple, dot push. And notice what this little structure that I'm building up on the right here, you notice that the latest thing I added is what's at the top of the stack, just like stacks in the real world, right? The last thing you add on the stack is the top of the stack. It's the first thing out. Last thing in, first thing out, okay? So let's just do that in Rex Tester. So I'm gonna add some stuff to our stack. Should we call our stack pancakes instead, just to unite it with the example on the slides? So I'm gonna add some pancakes to the stack. I'll say pancakes dot push Okay, and I'm going to add pancake 1 to the stack. Okay, pancake 1 as a string. Okay, and then I'm going to add pancake 2 to the stack. Sorry, dot capital P push. Whoops. And then I'm going to say pancakes dot push pancake 2 to the stack. Okay, and we can do the same for pancake 3. All right. So we've gone and added 3 pancakes to the stack. So when I run this, you can see it all works fine. So C# knows what we're doing here. And basically what that has done is it's created this structure in the computer. Okay, we've added 3 pancakes to our stack. And if we wanted to add a 4th, we would just say dot push pancake 4, right? Nothing too hectic. So what else is there? What else can we do with our stack? Well, just like with queues, we'll have these ideas of peak. Okay, so we have the idea of peak in stacks as well. Nothing too bad there. Okay, so we have the concept of peak as well. And we have a concept of pop. Okay, so pop is to stacks what DQ is to queues. So pop is how we remove from the stack. So when I say pop, the top thing is going to pop off the stack. So when I say bob.pop, pancake 3 is going to jump off of the stack. Okay. Now you can imagine, let's say if we're discussing this in terms of what this might look like for an actual pancake stack, is like you cook pancake 1, you cook pancake 2, and you're throwing them onto the stack on your plate. You cook pancake 3, and then when you say bob.pop, it's like you're eating pancake 3, and then let's say you cook pancake 4, so you dot push pancake 4, and then that would be your new stack. But now the next pancake you ate would be pancake 4, right? So dot pop is just going to pop the top thing from the stack. So the last thing you added is just going to pop off the stack. And dot peak will just show you what's at the top of the stack. So just like dot peak will show you what's at the front of the queue, when peak is used on a stack, it just shows you what's at the top of the stack. Okay. And then we also have dot contains. So peak and contains exactly the same as they are in queues. Dot contains will just tell you if the item you are looking for is somewhere on the stack. If it is, then it will return true. If it's not, then it will return false. Okay. And that's actually all we need to know about stacks, guys. That's all we need to know about stacks. So let's just go through these other few commands, see a couple of examples, really cement our understanding of that, and then we can jump on forwards to linked lists. Okay, cool. So we've pushed these 3 things to our stack. Okay, so pancake 1 was the first thing on our stack, then pancake 2, then pancake 3. Okay, so if I say pancakes.peak, okay, I'm going to print this out though. So I'll say console.writeLine pancakes.peak, okay, like so. So guys, this will just show me what's at the top of the stack. So what do I expect to see when I run this? And you guys, if you do want to type, you don't have to type the pancake. Don't worry about it. You can just type 1, 2, or 3. So just give me the pancakes number. Which pancake will I exactly? Okay. So, and you can see how that would be different from the queue, right? If this was a queue, then it would be the reverse, right? The first thing I added would be the thing that I see. Whereas with the stack, the last thing I added is the thing I see. Okay, so let's just run this to make sure that we are understanding correctly. Okay, so that's running. And you can see it prints out pancake 3. Okay, so let's print out on the next line as well, just to make sure we understand the difference between popping and peaking and all of that different kind of stuff. So I'm going to say pancakes.peak again on this line. So now this should print out 2 lines, right? Should print out 2 lines. And what will those 2 lines be, guys? What pancake / cakes will I see? 3, 3. Yeah, precisely. Precisely. Why? Because peak is not going to remove pancake 3 from the stack. It's just going to continually show me what's at the top of the stack, okay? Now we can try a few different options. So if I said pancake.pop, pancakes.pop, now what would we get? Anyone know? Chris has been carrying us through some of these questions. Can someone answer? So what's the difference now? What will slightly change about the stack? About what we saw, rather, about what we'll print. Hopefully you guys get the idea. Don't make me pick on you. Actually, you know, Chico, you were late, so can you answer? What's the difference now?
Okay. So the difference between pop and peak.
Yeah. Well, rather just tell me. So which pancakes will I see? Which two pancakes now will I see? So
you're gonna see pancake 2 and pancake 3.
okay, and in what order? Which will I see first? Which will I see second?
It'll be 3 first and then 2.
Okay, cool. Yeah, 100%. You've got it. Cool. Okay, so yeah, Chico's correct on that. So we're gonna see. Oh, sorry, I left out a character somewhere. Let me just. Cool. So pancake 3, pancake 2. Exactly. You're 100% correct. So the difference now was that pop actually removed pancake 3 from the stack, right? Whereas peak was just showing us pancake 3 twice. Okay. Cool. So I think you guys get the difference between pop and peak. As you can see, it's very similar to how queues were working, right? It's just like the opposite order. And dot contains is exactly the same as well. So dot contains, I can ask for a particular thing. So I can say like, does my stack contain pancake 2? And if it does, then it will return true. If I ask, does my stack contain pancake 4? Then that will go ahead and return false, okay? Because we don't have a pancake 4 on the stack. All right. So that's stacks. Hopefully you guys follow that. I don't think it's too different to how things were working before with queues. Actually, in fact, it's basically identical, just the reverse. So yeah, it's just a LIFO structure. So you've now seen a FIFO structure, first in, first out, and a LIFO structure, last in, first out. So the big thing about queues and stacks, guys, is the order. And hopefully that's come across to you guys now. The order that items are processed, all right? So whenever you're asked a question where you need a data structure that enforces a particular order, like either the first thing in must be the first thing out or the last thing in must be the first thing out, whenever you're dealing with a structure that enforces a particular order, you need to be thinking along the lines of queues and stacks, okay? Because these are very different from arrays, right? Because arrays allow instantaneous access anywhere, right? They don't have this weird concept of ordering, right? So now we should go ahead and discuss linked lists, which is the last data structure we have to deal with. Let me just check. Okay, cool, we're making good time. So linked lists are the last data structure we have to deal with in chapter 3. And we can see that, in fact, we have to start, in order to understand linked lists, we have to start by just refining our understanding of arrays even more. Because you can think like, okay, we've got stacks that enforce order, arrays allow instantaneous access everywhere. So why do we need linked lists? We seem to be able to do basically everything that we want to do. So why do we need a linked list? Okay, so we're going to jump back to this idea of an array, and we're going to discuss a little bit more what the disadvantages of an array are so that you can understand why linked lists exist. Okay, so we did discuss this briefly before, and you guys know already that when we're accessing an array, we start counting at 0. So the 0th item is the first item in our array. Then we have 1, then we have 2, then we have 3. You guys also know that arrays are, should I tell you the word or should I ask you guys for the word? There are 2 words, guys. There are 2 words that we use to define the concept of an array. Does anyone remember what those 2 words were, or even one of them? What were the two words that we used to define arrays, guys? Do you guys recall? Arrays are a data structure that is, yeah, so they're a data structure that is both and two very important words. They're to do with how the data is arranged and what the data should be, or what types of data there should be. Does anyone remember what those two words were? They're pretty big words, like weird words. Okay, I'll remind you guys. So they are contiguous and homogeneous. Okay, so what do we mean by that? We mean that they're all next to each other in memory, okay, literally, and they're homogeneous. They're all the same type. And I really want you guys to get why that is such an important thing to understand about arrays, okay? So when we're accessing an array, you guys know we start accessing it in 0. Then we access 1, then we access 2, then we access 3, okay? When you give the computer that number, you are pointing it towards a literal location in memory. So if you guys can understand, there's some memory on the left of our array, some memory on the right of our array, okay? And all of that memory is taken up. So all the computer is gonna store is the start of your array. The computer is gonna say, okay, the array starts here. That's 0. That's the position of 0, okay? So when you access 0, you say 0 times 32, and it essentially, so whatever this place in memory is, so we've got some number here, right? Some address, I'll represent it with like a hashtag, some address in memory, okay? So, forgive my terrible drawing. So we've got some address in memory, and we just take whatever this number is, and we add it to the address. So we've got our hash plus 0 times 32. And you guys can tell me what 0 times 32 is, right, guys? That's not too difficult of a mathematical question, right? 0 times 32 is 0, right? So then we're just accessing the address, because the address plus 0 times 32 will give us 5, right? Now, if we access 1 times 32, so we say we're looking into our array. Let's say this array was called nums, or n, okay? So let's say this array was called n. If we accessed n in position 1, okay? If we accessed n in position 1, the computer is going to take that 1. So likewise, last time it took the 0 and it multiplied it by 32. Now it's going to take the 1 and it's going to multiply it by 32, and it's going to add that to the address. So we have our address, which is just this place, this bit, that exact bit. Each thing is an integer, so they're all 32 bits. So we can multiply our number, whatever our address is, by 32. So we take 1 and we multiply it by 32. And then we arrive at this address, right? This address just before 6. And the next 32 bits are the number we were looking for, which is 6, okay? If we accessed in position 2, we would simply take that 2, throw it over here, multiply it by 32, which is 64, take our address, access at the address plus 64, and we would get over here, okay? And that would give us, the next 32 bits will be the 3, okay? So it'll be 32 ones and zeros that represents 3, okay? And likewise for 4, right? You would access, if you were trying to access 4, you would access it in position 3, right? The computer is going to take the 3, put it over there, say 3 times 32, add that to the address, and that'll give you this location just before the 4, and the next 32 bits will give you the 4. Now, this is great because it allows the computer to instantaneously access every single number in our array, right? Because all it has to do is one multiplication. It just has to say, you're accessing position 2. It just has to go, okay, 2 times 32, and it knows the exact address of 3, okay, of this value here, okay? And the only reason it can do this is because it knows that all the data is next to each other, and it's all of the same size, right? You can imagine if one of these was not an integer, let's say one of these took up 64 bits, then everything would be broken, right? Everything would be broken. You could no longer say 0 times 32, 1 times 32, and 2 times 32, because this would be at 64, but that would still be in the 6 if this was 64. That's why they have to be contiguous and homogeneous. They all have to be the same type, so that homogeneous, so that they're the same size, and they have to be contiguous so that they're all next to each other. Now that's cool because it allows for instantaneous access, but it creates a few problems, okay? It creates a few problems. And one of the major problems is that, so it gives us instantaneous access, but one of the major problems is that it's very difficult to add to an array, okay? So for example, let's say I wanted to add another item to the array. I wanted to add this 4 over here, right? Now, if I tried to access the array in position 4 in order to try and get this number, you can imagine it would go 4 times 32, which would point me to this address here, okay, where that purple line is, okay? 4 times 32 would get me here, right? 4 times 32. Okay, I should probably just type that one. 4 times 32 would get me like right there, right? 4 times 32, okay? Would get me here. All right. Now, in order to, you can see that that is not the correct address space, right? Because there's all of this free memory. I don't know how much it is. I don't have access to it. But there's all of this space here that is storing things not relevant to my array. So if I want to resize the array, if I want an array with 5 items, I literally have to go find another place in memory that has enough space for all 5 integers, okay, for 5 ints. And then I have to copy each of those ints across. I'd have to copy this one, and this one, and this one, and this one, and this one. I'd have to copy them all across into that new address space. And you can see that's very inefficient, right? In order to create a new array, takes 1, 2, 3, 4, 5, and the whole process of creating and finding that new place in memory. That's hugely inefficient. So this is one of the disadvantages of arrays. So arrays are great when you need instantaneous access, but they're bad when you're frequently changing the size of the array because you don't know how to access this thing without creating a new array entirely. Okay. So in order to create a new array, we would have to copy the old elements across and resize the entire array. So arrays have a fixed size regardless of the space that we actually end up using. Okay. Now linked lists solve this problem. So what we're going to do, we're going to take this little array here, this 5, 6, 3, and 4. And what we're going to do is translate it into a linked list. So rather than using an array, we're going to use a linked list. And then we're going to see how a linked list solves this problem of allowing us to add this extra 4. Okay, so that's what we're going to do now. So let's jump across and start understanding linked lists, which is the last data structure that we have to learn. And then we'll go ahead and take a little break. Okay, so just like the other things, the first thing we're going to do is create a linked list. And essentially, all that is this little structure here. When we create a new linked list, this is the structure we're going to be given. Okay, so I want to start by just discussing what this means. I think you guys already know the concepts of head and tail because you guys have seen it in queues, but I'm just going to remind you guys quickly. So what I am referring to when this structure appears, this thing here, is a pointer, okay? I'll use the word pointer. You could also call it a link, okay? But it's a pointer to a specific place in memory, okay? When we create a new linked list, and this is how we create a new linked list, okay, like that. When we create a new linked list, what it will do is it'll give us a pointer, which we'll call the head, okay, the head, which will eventually point to the front of our linked list. It's the head of the linked list. A nice way of picturing linked lists is like building a snake through memory. So this is almost the head of the snake, okay, the head of the snake, the front pointer, okay? And initially, that pointer is just pointing at nothing. And that's what I mean by null, okay? Null just means it's pointing to an empty place in memory, just nothing. So that's what we're going to do first. We're going to create this linked list. And what it's going to do is it's going to give us a head pointer that points to nothing. Okay. So let's go ahead and do that. I'm going to jump back to Rex Tester now and create this linked list there. Okay. So let's do that. I'm going to remove our stack. And we'll have to jump back to using system.collections.generic because linked lists fall under the generic namespace. So we're going to say linked list. Okay. And so initially I'm going to do it like this. So I'll say linked list We'll call our linked list. Does anyone have a name that they're volunteering for a linked list? Okay, no one does. We'll call it Bob. Good default name. Okay, so we've got linked list equals new linked list. Okay, like so. So this looks very familiar, right? When we were creating a stack and a queue and whatever. When creating a linked list, it's slightly different. You also have to use these arrows here. So right there, after the word linked list, we're going to put this set of arrows. And all I'm putting in the arrows is a type. Okay, and it can be whatever type you want. So I'm going to use ints, but it could also be strings. Okay, and all this is specifying is the type that your linked list will hold. Okay, so we're creating a linked list of ints, right? Because we want to store 5, 6, 3, 4. So we're creating a linked list of ints. So I'm going to say ints, ints. So this is a linked list that will hold ints. All right. So that's that. So that's how we create a linked list. Fairly straightforward, I hope. And you guys know all the types. You could make this literally whatever type you want, guys. So you can make it bools as well, whatever you want it, okay? So this is a linked list that will hold ints. And you can see when I run this, it works. So C# understands what we're doing here. And all this is doing is basically creating this little structure I have here. We've got the head of the snake, but currently it points at nothing because there's nothing in our linked list yet, right? We haven't added anything to it. We haven't actually done anything with the linked list yet. Okay. So now the next question is how do we start doing stuff with our linked list? Okay. Now, items are added to linked lists in what we call nodes, okay? And this is what a node might look like. So this is like maybe a representation for us to understand what the computer is doing, okay? So this is what a node might look like. Now, a node is just made up of 2 parts, okay, guys? So this whole structure together, this whole little structure together here is the node, okay? Those 2 little blocks together are the node, okay? And it's made up of two items, okay? We have this thing on the left here. This is the value, okay? So this is what we call the value or val, okay? So value. And this over here is another pointer. Now, as I said, you can, a good way to think about what we're doing here is to think about it as if we're creating a snake through memory. Okay, a snake through memory. So the snake is made up of several nodes, okay? Several nodes. And each time you add an item to the snake, to this linked list, you are adding a node, an entire node. And a node will always have these 2 parts to it. It has a value and it has a pointer, okay? So the thing on the left here is the value. The thing on the right here is another pointer. And this pointer is just like the head pointer of our snake, right? It just points to another empty place in memory. You guys can see it's still pointing to null, okay? It's pointing to another empty place in memory. And what this pointer is pointing to is the next item in our linked list, the next item in our linked list. That's what it's pointing to. So currently there is no next item because we've only added the 5. But what we would do next is add the 6, right? What we would do next is add the 6. So we would replace that null place in memory with another item, okay, like so. And that item is made up of the same 2 things, right? It's made up of the same 2 things. This node also has a value, it's 6, and it has another pointer pointing to the next place in memory, okay? And you can see that pointer for now points at null. And what we would do next is add another node where that null location in memory is, where that empty location in memory is. And likewise, that node is made up of a value and it's made up of a pointer, right? And that pointer points to null. And when we want to add another item, we would add it like that. And how we add it, what the command is .add last. So every time we add last, it'll take whatever we specify an item and it'll add it as the value of the node, okay? And every node will always have these 2 things. It'll have a value and a pointer that points to the next item, okay? So 5 points to 6, which points to 3, which points to 4, okay? And hopefully you guys can already see how this solves our problem. right? Now, if I want to add another thing, these things don't have to be next to each other in memory, right? Like here it looks like it's pointing close by, but you can imagine that this can be anywhere, 5 can be anywhere in memory. It doesn't have to be next to 6, because wherever we add 6 in memory, 6 can be anywhere in the computer's memory. 5, the pointer from 5 can go all around the computer's memory. It could go very far and eventually land up at 6. It could point to 6, okay? They don't have to be next to each other at all. The pointers can point anywhere in the computer's memory. So they don't have to be next to each other anymore. So when we want to add another item, it's as simple as just taking whatever the last pointer is and just pointing it to the item that we're adding. So if we're adding another 4, we would just add another node that holds 4 as its value and holds another pointer that just points to null. Okay, and so it's simple. It's as simple as that to add another item. Okay, so that's how this solves our problem with arrays. All right. Cool. So let's go ahead and create up the structure in C# over in RexTester. So I'm going to say bob.addLast. Okay. And you can see there are a couple of other options. Like when I hit add, you'll only really be tested on add last, but you can add after. So like specify a certain place to add it in the linked list. You can add it as the first item with add first, or you can add it as the last item with add last. Okay. But either way, it's always just adding what you want. And we can say 5634 is what we're going to add. So I'm going to say bob.addLast 5, bob.addLast 6, bob.addLast 3, and then bob.addLast 4. Okay. Okay, and so that's how we build up our linked list. And you can imagine now adding that next 4 is as simple as saying bob.addLast, and we could add another 4 or whatever we wanted, and it would be able to do it instantaneously, just like adding all the other items. And it doesn't matter how large this linked list gets, because they don't have to be next to each other. There's no cap on the size other than the whatever space there is in the computer's memory itself. But yeah, that's how we could build up that array in a linked list. Okay. Cool. But now how do we actually access it, right? Because now there's this problem of all of this stuff is not next to each other in memory. Okay. And that's actually it's an interesting question, quite a tough thing. Okay. But let's build up even more of an understanding. Okay. What I'll do, so yeah, we'll see it now. So let's say I want to access 5. All right. That's going to be easy. So we have the head of our snake, okay? That's in our code, we basically called that Bob, all right, Bob. That's basically what we called the head of our snake. It's the name of the linked list. You can think of it that way. So we have access to the first item. We have access to this pointer over here, okay? This pointer over here, okay? Through that pointer, we have access to this first node that holds 5, because you can see the pointer points directly at this node, okay? So I could say bob.first, okay? And that specifies the first node. So what I'm going to do, I'm going to jump over to RexTester and do that. And we're going to see what it prints out, okay? We're going to see what it prints out. So I'm going to say console.writeLine bob.first. So I'm just going to see what that does. So I'm saying bob.first, okay? You can see, you see what it printed out here, guys. So it says system.collections.generic.linked node. You see that word node? That's what we've been discussing, right? The node has 2 things. It has a pointer to the next item, and it has a value. Okay? Has a pointer to the next item, and it has a value. So what do you think, just based on how things have been named and done prior in C#, do any of you guys have a guess? And it can be a guess. I understand you guys haven't seen it yet, but it might be quite cool if you guys can predict. So I have this node now. You've seen that bob.first gives me the first node. It gives me this. If I wanted to access the 5 in this node, what will I access? So I'll say bob.first.what? What will I be accessing to get that 5? When we look at this structure? Yo, nice, Chris, yes. So we'll say bob.first.value. And we'll see that's going to give me 5. Okay. So that's cool. So it seems to be working how we want it to work, but we have this weird question now of like, how do I get, so we can see where we are in like this little internal representation, right? What we did, we said Bob, that was like the head. We said dot first, so that was like following this pointer to get to this node. And then we said dot value, which was like going and getting the 5, because that's what's in the value of the node, right? So that's what we did now. We said bob.first.value. But now if I want to get the next thing, so let's say I want to get the 6. How am I going to get to that 6, guys? How will I get to that 6? We'll have to say bob.first, so that'll give us to this node. So what am I going to do next to get to the 6? What am I going to do next to get to the 6? Because we can say dot value to get to that 5 over there. But how will I get to that 6, guys? Because we can't like just jump, right? That's the problem. With the linked list, we were able to just jump. I mean, with the array, we were able to just jump around, right? I could just access it in position 1 or 2 or 3, and I could instantly jump around between the array. But now you see, I have to follow this pointer. I have to follow the sequence of pointers. I can't just jump around how I like. So what would I say? I would say bob.first. If I say dot value, that will give me the 5. So how will I instead jump to the next node, guys? How would I instead jump to the next node? Just look at the diagram and see what you think. And again, it can be a little bit of a guess. How am I going to jump to that next node? So we say bob.first dot what? Dot what? Okay, so guys, you can see it at the bottom here. Dot value gave me the 5. Dot next will give me the next node. So what I'll do is I'll say bob.first.next, okay? And what that will give me is this next node. So it'll put me like over here, okay? So let's go see that in the code. Okay, so I'll jump over to the code. Let me just erase this so we don't have okay. So I'll go back to Rex test. I'm going to say bob.first. Instead of dot value, I'm going to say dot next. Okay. And let's see what that prints out. So we'll run it. You can see it gives me another linked list node. So guys, how am I going to get the 6 out of this? So I said bob.first.next dot, how am I going to get the 6? Once, yeah, exactly. Yusuf, Chris, you're both correct. We'll say bob.first.next.value. And you guys will see that'll give me the 6. Okay. So you can see how I'm jumping around through this linked list. It is literally like a snake, right? You have to work with it like a snake almost. So it's going to say, so we say bob.first, okay, dot next. And then when we said dot value, that gave us the 6, all right? And likewise, if we want to get the 3, we're going to say bob.first. That's going to bring us here. Dot next is going to follow this to here. Dot next is going to follow this to here. Okay. And then if I wanted to get the 3 out of that, I would have to say dot value. Okay. Likewise, if we want to get out the 4, we're going to have to say bob.first. That will bring us here. Dot next will bring us to this guy over here. Dot next will bring us to this guy over here. Dot next will bring us to this guy over here. And then dot value. Okay. Quite a mission, hey? So you can see that the array gave us instantaneous access. In order to access anything in this is clearly not instantaneous, right? It takes a while. You have to go dot next. The computer has to do quite a few operations to get from the first item to the last item. In the array, it was very simple. In the array, you could just say access it in position 3, and the computer instantly knew where in memory to look. Okay. Whereas now we have to like start at the head, and because it's all over the place in memory, we have to go dot next. But the advantage that this gives us is that we can make this structure any size we want. If we want to add another thing, we can add it wherever we want in memory, and it will just work. Okay, cool. So this structure is what we call a singly linked list, a singly linked list. Okay. So yeah, there's just one more idea that I have to explain to you guys. It'll be brief, but yeah. So this is what we might call a singly linked list. And I say singly, that's what I mean, singly linked list, like that. Okay, singly linked list. Okay, why do we call it this? It's actually quite simple. It's because there's a single link between each node. Okay, there's a single link. But what this means is that there's no way to get back. Okay, so like, let me try to visualize it for you. Let's say we have some code and we go, okay, we jump from first to next to next. Okay, so we're at 3. Let's say I want to now go back, like something happens. I want to go back and I want to see what was before the 3. You guys see there's no way for me to get back, right? There's only a next. If I wanted to get back to the previous thing, I would have to start at the beginning, and like keep track. Okay? So I'd have to start at the beginning and keep track of how many jumps I did, right? So there's no way to go back in a singly linked list. Okay? This is not how C# does a linked list. Okay? In C#, the linked list is actually a doubly linked list. And it's not a difficult idea to understand, this idea of a doubly linked list. It's very much the same. Okay? All it means is that each node in a C# linked list actually has 2 pointers. Okay? It has a pointer to the next item, and it has a pointer to the previous item. Okay? And it's fairly simple to like adjust our little example here to reflect that. So every node, it's not just .next, there's also a .previous, okay, that jumps back. Okay. And if you understood .next, and then likewise, this last one will just point to null. Okay. There is also a thing called a circularly linked list, where the last item points back to the first one, because it's creating like a circle, if you like. All right. But we don't have to worry about that. We just need to worry about doubly linked lists and singly linked lists. So a doubly linked list, it's the same, except there's also this previous pointer. Okay. There's also this previous pointer. So let me just show you that in the code, and I'm sure it'll instantly make sense. So what we're going to do, we're going to use the previous pointer. I'm going to say .next. Let me erase that. So I'm going to start at the front, obviously, so at the head. I'm going to say .next to get to the 6, .next to get to the 3, and then I'm going to jump back. I'm going to say .previous .value and get to the 6. So we're going to say next, so first, next, previous value, okay? And we're going to get 6. All right, so let's just jump over to the code and I'll show you that, and then we will be done with linked lists. So I'll say bob.first.next.previous.value. So what did that do? It said bob.first, that got me to the first node. So that would be the 5. .next got me to the 6. .next got me to the 3. .previous, I move back to the 6. .value, I print out the 6. So I'm going to say run it. And you can see that that gives us a 6. And if I hit .next again, okay, can someone, it's pretty complicated, this one. Can someone run through? What integer am I going to get at the end of this whole line? Take your time. Would I get 5? Should we run through it? Let's run through it. So I say next 3 times and then previous. So let's see what happens. So we'll draw it. We'll draw it out. So I'm going to say bob.first. That brings me here. .next, that's once. .next, that's twice. .next, that's 3 times. .previous, .value. So it's going to give me a 3. Okay, it's going to give me a 3. So let's try that out. Make sure that we're getting it. Cool, so it gave me 3. All right, shall we try again? What happens, guys, if I add a .previous over here? can see this chain is getting quite long, right? It's getting a little bit hectic. Okay, exactly. Cool, I think you're getting it. So yeah, that'll give me a 6. When I run it, it gives me a 6. Okay, and you can see I could do .next again after this, and that'll jump me back to the 3, right? See, and then I'm at the 3. Okay, so it's pretty interesting, and you could like build up a picture in your mind of how this is working, and always work through the linked list. Okay, so that's that, guys. That's linked lists. Those are the 4 data structures that you need to know. And now there's just one more thing to cover. And then you guys will be at the end of essentially first year university computer science after this next set of slides on what we call sorting. And it ties in quite nicely with these ideas of data structures. Okay, but that was linked lists. What's the big advantage of linked lists, guys? Is that it allows us to very quickly insert and delete items. Because you can imagine, let's say I wanted to delete something as well. If I wanted to delete the 6, I could just say cross it out, and I could just point the pointer to the 3 instead, and then the 6 is gone, right? If I wanted to delete the 3, I could just take the pointer from 5 and just point it to the 4, and then the 6 and the 3 are gone. Okay, so it allows us to quickly insert and delete items wherever we want, because we can just we can just point around things. We can always just point to the next thing. Okay. Whereas arrays didn't allow for that. But what's the disadvantage of a linked list is that it takes very long to access items. Okay. If you're frequently accessing all these middle items like 6 and 3, then you have to go like .next, .previous. It's a bit of a hassle, right? Like accessing the items. Okay. So those are the 4 data structures we have. Hopefully you can see what their advantages are of like these various data structures. And you've built up a bit of an understanding of why we have all these different data structures. Okay, cool. So with that, we can take a little break now, I think. We can do a 10-minute break. We'll come back at 10:05 and then move on with sorting, the last part of chapter 3. Okay. And after this one, I'll have a little recommendation for a Rex tester challenge that you guys will have to do. But for now, I'm going to go grab some water. If you guys have any questions, feel free to post them in the chat while I'm gone. And I'll get to them when I get back, okay? Cool, I'm back. But obviously I won't start immediately. I do have a Mentimeter quiz for us to do, just to cement our knowledge of data structures. Ooh, what happened? Okay, it's fine. So you guys can join this while we wait, if you like. So you can go to menti.com, and the code today is 3686371. 3686371. And yeah, can join this. Oh, wait, what happened? This little Zoom pop-up is a little bit annoying. I don't know how to get rid of it. Hide floating meeting controls. That seems sensible. How do I bring them back now? Oh, lol. Bit of a mess up. No, I don't have the meeting controls. Oh, that's funny. Oh, well. Can I right-click this and say... Huh. Okay, maybe I shouldn't have clicked that so rapidly, because now I'm very confused about how to continue. Oh no, that's annoying. Is there a hotkey for reopening the Zoom controls or something? Hotkey for Zoom. Control-Shift-Tab, Control-Shift-H. Control-Alt-Shift-H. Control-Alt-Shift-H. Okay, they're back. Cool, okay, so that's useful to know. Huh. Ooh, you can rejoin, by the way. I saw that someone joined, but then they're gone again. Hopefully we get more than one participant. We should have, what, 4 people, right? So AB, Chico, Taffy, Yusuf. Ooh, where did Chris go? See, didn't WhatsApp me. Okay, I see you're back. So yeah, we should have 4 people. So I'll wait for you guys to get in.
Okay, sir, I'm coming now.
Cool. Okay, they do show there. Cool, one more person. Not sure who it is. I'll give you a couple of more seconds to join, maybe like a minute or so. We'll start at 10:05, obviously, because that's when the break was supposed to end.
Yeah, I'm on the thing. Okay, let me type it.
Cool. Great, so shall we get started? Shouldn't be too tough since a lot of it we just learned, but let's see how it goes. Okay, so question 1. A data structure in which the last item added is the first item removed. So which one is that, guys? Last item added is the first item removed. Only 25 seconds left. Ten, 9, 8. Cool. Cool, everyone got it? Not super surprised about that. That one's not too bad, I don't think. I see one person might have disconnected. That's a pity. Cool, question 2 of 5. I want to see what the next item out of my data structure will be, but not actually remove it. Which command should I use? I want to see what the next item out of my data structure will be, but I do not want to actually remove it. Okay, everyone got it again? Not super, I suppose this will come down a lot to who's fastest here. Okay, let's see. But this is the style of questions that you'll often be given about these sort of data structures. Data structure in which the first item added is the first item removed. The key is wording, right? Just make sure that you are following on the wording. First item added is the first item removed. Ooh, 2 people said arrays. So remember, guys, whenever we're talking about order, we're always thinking about either stacks or queues, right? So a queue is FIFO, first item in, first item out. A stack is LIFO, last item in, first item out. An array has no particular ordering. You can access arrays in any order you like, instantaneously. Okay. Cool. Which 2 commands add and remove items to and from a stack, respectively? So which 2 commands add and remove items to and from a stack, respectively? Oh, okay, Chris's power went out. That's horrible. Okay, push and pop. Yeah, add and remove are not commands, guys. They're not commands. So push and peek would add to a stack and show you what's at the top of the stack. Append and pop also don't exist. Pop would remove from a stack, but append is not a thing for stacks. Push and pop are correct. Add and remove are just tricks. If you guys remember the slide when we were showing stacks, add and remove were not included on it. Okay. Cool. And the last one, this one's pretty tough. Using valid C# code, complete the following to remove an item from the queue, called my queue. So use valid C# code. Notice the semicolon is already there, and you actually have to type in what's the command you would type, how is it spelt and stuff, what's the command you would type to remove an item from the queue. To remove an item from the queue. Wow, someone's already answered. That's cool. Yeah, some extra time on this one. I gave like 1.5 minutes or 80 seconds rather. Okay. Two answers. That's cool. This one's tough because we did learn it last week, but I did remind you of remind it to you guys, or remind you guys of it at the start of the lecture. Okay, right lined up, pop, list, T. Oof, some tough ones. The correct answer is DQ. I see someone got it. That's very cool. Nicely done. Nicely done. Dot pop would remove from a stack. I'm not sure how right line got in there. List T. That's how we might create a specific type of list, but yeah, DQ is 100%. Nicely done. I think most of this would come down to how well you remembered last week's lecture. Okay. Cool. Okay. Great stuff. Taylor Swift, congratulations. Taylor Swift and Chico were pretty close. Wolfmaster got the same amount correct, but a little bit too patient. Need to trust your guts more. Answer strong and yeah, answer quickly. Okay, but congratulations to Taylor Swift. All right. Nice, Yusuf, nice. Okay, yeah, no, I mean, what was that? 3 right, that's pretty good, that's pretty good. Who got the DQ at the end? That's quite cool, because I think that one's pretty tough, because typing questions we're not used to. Okay, cool, nice, nice. All right, so I think let's continue. So yeah, sorting. This can be pretty tough conceptually, but but don't worry, we'll talk through it, and it's very cool to understand this. This will be like the first large algorithm that you guys are learning. It's the first like major algorithm that you guys are learning. Okay. So the first thing is to just answer, what is sorting? What is sorting? Sorting just means arranging systematically into groups. Okay. So, or separating according to type. For us, for computer science, that definition doesn't really do us as well. In our case, it's more like arranging into a predefined order. Okay, arranging into any predefined order is what we mean by sorting. Okay, so with an understanding of that, we maybe should just discuss like why we're learning this in section 3. Because it's a bit confusing, right? Because we started by covering the application lifecycle, then we covered data structures, and then we covered sorting. And to be honest, I'm not sure why the application lifecycle is in the same part as data structures and sorting, but it makes a lot of sense that sorting and data structures are together. Okay, makes a lot of sense that sorting and data structures are together, because sorting is something that we do on data structures. It's one of the ways that we work with data structures. So for example, let's say I have this array on the left. We worked with this array a little bit while we converted it into that linked list, if you guys remember. But let's say I have this array on the left, 5, 6, 3, 4. Sorting this array would mean that I program the computer. I tell the computer, I explain to the computer how it can convert that array into 3, 4, 5, 6. So arrange it in ascending order. I could also arrange it in descending order, right? 6, 5, 4, 3. So I could do either, I could do whatever I want, but the point is I'm arranging it into a predefined order, all right? Likewise, if I have this array of strings, I could arrange the strings into alphabetical order, in reverse or forwards, okay? So that's sorting, and you guys can see we have these data structures, and this is one of the ways that we order and work with those data structures. We call it sorting. Okay, arranging into any predefined order. All right. Now you have to remember these arrays can be very large. So here we're working with like play arrays, but you can imagine when you're a programmer at an actual company, if you have like a database that has 1 million users and you want your 1 million users' names to be arranged in alphabetical order, you can imagine that that's a fairly large array, and they can get much larger than that, right? If you're working with sets, huge amounts of images or any kind of data. Like GPS coordinates, any kind of thing like that, these arrays can be gigantic, very, very, very large. And so the approach that we use for sorting must be automatic, it must be fast, and it must be memory efficient, okay? So the main thing is that we want to program the computer to be able to do this, all right? So for a human being, it's very easy to see like, okay, 3 must be at the beginning, then 4, then 5, then 6. And we don't even really know how we do it, right? Like in our brains, it just happens, right? You just know that 3 is at the beginning. There's no like set algorithm that you're necessarily following. You just do it, okay? It's intuition. It's very natural for us. But when explaining to a computer how to do this, it's slightly more complicated, okay? It's slightly more complicated. So that's what we're going to do now. All right. I should perhaps tell you guys where this stuff is in your textbook. We'll do a slightly different variation on the algorithm than the one that is in the textbook. I'll save the one that is in the textbook. Maybe you guys can program it up yourselves when I give you that Rex tester challenge or kata for you guys to try out. But we're sort of considering what's happening on page 78, if you guys are interested in looking in the chapter 3 PDF, okay? The chapter 3 PDF that was shared on the WhatsApp group by Arthur. Okay, this would be on page 78. Okay, so before we jump into sorting, I just want to make a quick simplification, and it should be fairly straightforward. So if you think back to that eye-comparable interface that we learned about at the beginning of chapter 2, any 2 items that I have, people, rectangles, dragons, golems, any 2 items that I have, I can compare in some way, right? We can define that order of they're either equal, the one is before the other, or the one is after the other, right? We can define this order for any group of things, okay? So for simplicity, we are not going to consider those kinds of complex objects. The sorting algorithm is already complex enough. And so we're going to focus on how the sorting algorithm works instead. So all we are going to consider, we are simply going to consider an array of integers, okay? We are considering an array of integers. The sorting algorithms we learn through some clever modifications can be adjusted to work on different data structures. They can be adjusted to work on different types. But we are focusing on an array of integers, okay, just for simplicity's sake. So don't get too bogged down in that. You don't need to know how to convert these into other options, okay. Cool. So what we'll start by learning is a fairly straightforward but very, very clever, very intuitive algorithm called BubbleSort, okay, BubbleSort. BubbleSort is what will sort an array. It will sort the array using a sequence of comparisons and swaps. And I want you guys to remember those 2 words, comparisons and swaps. And we'll go through the algorithm together, and you'll see exactly how this is done. Okay. So we are going to start with this array over here. Okay. So you guys can see I have an array called 82413. Now, if I ask you as a human to sort this array, it's very easy, right? You can see intuitively, if I sort the array in ascending order, it would be 1, 2, 3, 4, 8, right? You can just see it. Like how it happens, we still don't know, right? It's almost like a psychological question, but you can see how the array should be sorted. You can imagine if this was a list of 1 million or 1 billion integers, then it becomes extremely difficult for a human being to sort that array, right? But for a computer, that's still easy. Okay, once you've got this little algorithm that we're doing. But what we want to do is explain to a computer in a sequence of steps how it can sort this array, how it can sort the array, rather than relying on our own intuition and our own abilities, okay? So how can a computer do this? Again, BubbleSort is one way. It's one algorithm for doing this, and that's what we're going to learn now, okay? It will do it through a sequence of comparisons and swaps, okay? So what's a comparison? Well, we're going to start. So you can see that blue line just appeared. It's underlining the 8 and the 2, okay? That blue line just appeared. It's underlining the 8 and the 2, okay? That is going to represent a comparison. And all I'm going to say is, so what this means is we're asking a question. This will tell us whether or not the thing on the right is less than the thing on the left. Okay? That's all it's going to tell us. Is the thing on the left less than the thing on the right? Or the other way of wording the question, very similar, you could say, is the thing on the left greater than the thing on the right? That's the question this is answering. Okay, so is 8 greater than 2? And I know it might seem silly, but I want you guys to focus. I want you guys to answer each question yourselves, because it might seem straightforward, but once we put all these steps together, it can become, you know, it's more complicated, okay? So that's a comparison. The answer to this question, guys, so it's a true or false question. In this case, is it true or false? What answer do I get? Is 8 greater than 2? That's it's true, precisely. How would we answer this question? How would we ask this question, rather? In code, what would I say? Do you guys remember? What operator would I use? What operator would I use? What's the line I would type necessarily to do this little comparison? We might say something like, if 8 is greater than 2, right? Obviously, we want to make that general, so we would want to use the positions. So it's more like, if numbers in position 0 is greater than numbers in position 1, assuming our array was called numbers, for example. Okay, but let's continue. So let's see what happens. So we'll ask this question, and maybe you guys have some idea of how we might ask this question already. We'll ask this question, is the thing on the left greater than the thing on the right? Okay, if the thing on the left is greater than the thing on the right, then we're going to swap them. Okay, so as we've just discussed, this will work through a sequence of comparisons and swaps. So we're going to do a comparison. Is 8 greater than 2? So 8 is on the left. It is, right? 8 is greater than 2. So we're going to swap them. Okay, that's the rule. If the thing on the left is greater than the thing on the right, we swap them. Okay, and that's one comparison and one swap. Okay, now the question, you might say, okay, cool, this looks fairly straightforward so far. We can just swap them, right? But actually swapping elements is slightly more difficult than you assume. And so let's think about that for now. So let's focus on that question for now. How are we going to swap elements? Okay, so what I'm going to do, I'm going to construct a little example for us. We're going to have two numbers. I'm going to say int x equals 8 and int y equals 2. Okay, and I'm going to print out 2 lines at the end here. Okay, so I'll say console.writeLine, console.write. And I'm just going to I'm going to print out, so whatever the value of x is and whatever the value of y is, okay? And I'm just doing it in a slightly fancy way. Hopefully that works. I think that's how we do it in C#, if I remember correctly. So this is a very simple piece of code. This might look a bit freaky to you guys, but all it's doing is, by putting the $sign there, whatever variable I put inside these curly brackets is read as a variable rather than as just the string. So that's taking whatever the value of y is and it's putting it inside the print statement. So that's all it's doing. And you can see all this does, it prints out x and then whatever the value of x is. So x is 8 and y and then whatever the value of y is. But you guys don't have to remember this fancy printing style. You don't have to remember that. That's not what we're concerned about. The only thing I'm doing here is showing you guys what the value of x is and what the value of y is, okay? So you can see initially x is 8 and y is 2. Now, guys, I want to get it to a place. So let's say I don't want to just say x is 2 and y is 8. I don't want to do it that way. I want to swap the values of x and y, okay? I want to swap the values of x and y. So by the end of this, I want x to be 2 and y to be 8. Or I want whatever x's value was to be in y, and whatever y's value was to be in x, okay? For any numbers, Okay, so how would I start this, guys? What's maybe the first step you would consider doing? Does anyone know? And feel free, guys, to guess, because this is going to be a thinking thing. We're going to work through this together. I think that's the best way for you to understand. So what's the first step I might do, right? I want X to take on Y's value. Let's start there. How do I make X take on Y's value? Do you guys remember? It's fairly simple, right? If we just consider that isolated case. How do I make X take on whatever value is in Y? You guys know the operator that I would have to use, right? I'll wait for you guys to think about it a little bit, perhaps. How would we do it? It's the same as what we've done over here, right? So we would simply say X equals Y, right? That's a good starting point. Now, that's fine, right? But now, how would I make Y take on X's value, guys? What line would I type? What line would I type in order to make Y take on X's value? So we've made X take on Y's value. How would I make Y take on X's value now? X equals Y. So you can see if I run this now, so you see previously X was 8 and Y was 2. Now they're both 2. Okay, because X equals Y. So how do I make Y take on X's value? You might say something like Y equals X. This is like how a human might think about the problem. But what problem are we running into here? You can picture like, let's just think about the problem diagrammatically. Okay. So we have some variable over here. So let me quickly just jump back to before we did the swap. Okay, before we did the swap. So we have 8 stored in memory somewhere, right? We have 8 stored in memory. So let's say I have this, I have these 2 locations in memory. Okay, let me represent it to you guys like this. So I have one location in memory and a second location in memory. Okay, one of them is holding 8, the other is holding 2. Okay, so 8 and 2, right, left and right. I want to swap them. So whatever is in this location on the left, I want it in the location on the right, and whatever's in the location on the right, I want it in the location on the left. Okay. How do we perform this operation? How do we make this occur? Let's say, so we're just calling it X and Y, but in reality, it's like numbers in position 0, numbers in position 1. However you're referencing it doesn't really matter. I want to talk about how we actually swap it as a human being, right? So one obvious option, like what we just said, like if this was called X and this was called Y, right? We might just say, okay, X equals Y. So what I would do is I'd say, okay, X is gone, and Y is, and it just becomes 2, okay, whatever Y's value is. So I just moved Y's value there, okay? And now I wanted Y to be, what did I want it to be, guys? What did I want Y to be again? Someone post in the chat. What did I want Y to be again? We wanted to swap them, right? So like if I undo a little bit, I wanted Y at the end to be 8 and X at the end to be 2. So I got to this place. How do I set Y to 8? I wonder if this is getting, it's almost a little bit too abstract. So remember, you have to think like a computer. Okay. So the issue that we're running into here is that we as humans have a memory. Okay. We have a memory. So like you can picture here, we said 8. Okay. When we said X equals Y, what did the computer do? It took the thing on the right, this Y, and it saved it in the thing on the left. So all it did was it went, okay, 8 is gone. I forget about 8. I forget about 8. And I make it 2. Okay. The issue with this is the computer has now totally forgotten, totally and completely forgotten what was previously in X. Okay. So I hope you guys understand that. And you could imagine if we did it in the reverse. So let's say if we have 8 here, you get the same problem if you do it in the reverse, right? So if I, instead of saying X equals Y, I say y equals x. Okay, so instead of saying x equals y, I say y equals x. You can imagine that the 2 over here is just forgotten, and y just becomes whatever is saved in x. So it just becomes 8. Okay. So do you guys see the issue that we're running into here? It's that the computer has 2 locations in memory. It has enough space to represent 2 integers. It has int x and int y. But how many spaces, let me ask you this. How many spaces in memory do I need to swap these 2 items? Like, as a human, it's difficult to intuit about the problem in that way. But how many spaces in memory will the computer need to actually swap the value of x and y? Do you guys know? How many? Just say a number. 4? Would it be 4? So let's try it, Yusuf. Let's try it. So we have x, y. Okay, we want to swap their values. At the end of this, x must be 8 and y, at the end of this, x must be 2 and y must be 8. Okay, that's what we're trying to get to. Okay, we're just trying to swap the left and the right. Okay. So the problem that we ran into first in trying this with just 2 places in memory is that when we forget the 1, so if I set x to y, then x just becomes 2. And now I've forgotten what I need to set y to, right? I want to set y to something, but where is it? It's gone, okay? So let's try a simple thing of just saying, okay, I'm going to create a 3rd place in memory, okay? And let's just, whatever, we'll call it z or something, doesn't matter, okay? And what I'm going to do is I'm going to save x there. So I'm just going to be like, okay, x, that's what I'm replacing, okay? Now I can say, okay, x equals y. So I erase it. I go like, okay, that's done. So x is now y. And now when I want to set y to what x was, initially I had this problem, like I had forgotten what x was because I overwrited it. But now I can say, oh, y must be set to 8. Okay. So this is quite a cool thing. Yeah, exactly, Yusuf. So this is like quite a cool thing, like on a philosophical level. And now I can forget z, right? I don't need it anymore. I only needed it temporarily, okay? And for that reason, what we call z is a temporary variable. We call it a temporary variable because we just need it temporarily while we figure out what we need to store, okay? So the interesting problem that we ran into here, and it's quite a cool idea, right? It's like nice to see the differences in how computers and people think. When we were swapping 8 and 2, it became this weird problem of like, for a human being, this is as simple as just going like, oh, just swap them, right? We could just be like, oh, okay, we just swap them, right? 2 is there and 8 is there. We don't really know how we do it. We don't really care how we do it. It just happens, okay? You just swap 8 and 2. You don't have to forget anything or do anything like that. But for a computer, on a logical level, you need that 3rd place in memory, right? Like when swapping this, it's not as simple as just saying, oh, 8 becomes 2, 2 becomes 8. It's not as simple as doing that. You need this 3rd place in memory. You say, okay, the 8 goes over here because that's what was in the left. Then we swap out the 8s with the 2, and then the 8 jumps back in over there, okay? That's how the swap actually occurs on the logical level. Okay. So if we want to see this in code, when swapping int x and y, so I can't just say x equals y and y equals x because that makes no sense. They both end up as 2. We've just forgotten what we were saving. So what I'm going to do is I'm going to say int temp. Okay, so I'm creating this temporary variable. Temp just stands for temporary. I'm going to set it to x. Okay. Then I can set x to y, and I can set y to temp. Okay, and then when I run this, we say at the end, x is 2 and y is 8. Okay, so that's how we swap. When we say swap, that's what we mean. Okay, it's slightly more complicated than you might initially expect. It's not as simple as just saying x equals y, y equals x, because you've forgotten something when you try to do that. So you have to create this temporary 3rd place in memory that you save x in. X equals y, y equals temp. And this is just literally that little picture we had, guys. So we initially had x and y. So we have x, we have y, We've got 8 at x at the initially, so that's what this first line is doing. It's creating 8 in x, and y, and that second line, int y equals 2, is creating this. Then we say int temp equals x. So what that's doing is it's saying we create this third place in memory called temp, okay, temp, and we save x at that place. So that's going to be 8, okay? So int temp equals x. That's what this is basically what that line is doing. Then we say x equals y. So that's like, okay, so we take whatever's in y, it's 2, and we replace x with that. So x becomes 2. And then we say y equals temp. So whatever was in temp, 8, is what y becomes. Okay, so that's what we're doing there. It's like a little trick, basically. Okay, so that's how we swap things in code. That's how you swap two numbers. You require 3 places. Okay. So it's an interesting little problem, quite a cool way to think about the differences in how human beings and computers operate. Okay, cool. So when we swap 2 and 8, that's how we do it, right? We save 8 in the temporary variable, we overwrite 8 with 2, and then we overwrite 2 with whatever's in temp, and then the swap has occurred. Okay, and now we're on to the next step. The next step is we just move up the comparison once. Okay, like that. So we compared the first 2, and remember, BubbleSort works on a sequence of comparisons and swaps. So we now do the next set of comparisons and swaps. Okay, so we say, okay, the next comparison is comparing 8 and 4. Okay, so we ask the question: is the thing on the left greater than the thing on the right? Okay, if the thing on the left is greater than the thing on the right, then we are going to swap them. Okay, the same rule. So this was the same rule, right, guys? We said, is the thing on the left greater than the thing on the right? If they are, we swap them. We do the next comparison. Is the thing on the left greater than the thing on the right? It is. We swap them. Okay, and we repeat this process again. So the blue line is going to move up. We do another comparison. Is the thing on the left greater than the thing on the right? It is. We swap them. Okay, and how does that swap occur? Well, we'll save 8 in the temporary variable, right? We'll override 8 with 1. And then we'll override 1 with whatever was in the temporary variable, which was 8. And then the swap would have occurred. Okay, and then we move up again. So we go, cool, is the thing on the left greater than the thing on the right? It is. All right, we swap them. How did that happen? We saved 8 in the temporary variable, override 8 with 3, override 3 with whatever's in the temporary variable, and then the swap occurs. Okay, and that's one pass of BubbleSort. Okay, you can see that the list is not sorted yet. Okay, so there's more steps that we have to do more than this, but that's one step. Okay, that was one pass of BubbleSort. We passed over the entire array, and that was one pass. Now, what happened? Okay, and this is quite cool. So this is how BubbleSort gets its name. So you can see BubbleSort is a little bit of a weird name, right? Like BubbleSort, you know, where does that come from? Seems a bit strange. So the name BubbleSort comes from like the same idea, like if you're underwater, I don't know if you guys have ever done any like scuba diving or snorkeling or whatever. When you're underwater and you like spit out a little bubble, like breathe out a little bubble, the bubble floats to the top, right? The bubble like rises to the top. And this is where BubbleSort gets its name. So at each step, the largest number in the list will bubble up to its correct position. So we can see this. So you see 8 was initially the first item in the list. 8, we know, as humans, you can think about this. So 8 is supposed to be the last item in the list, okay? What BubbleSort will do is the 8 is going to bubble up to the top. It's going to bubble up to its correct position, okay? You guys see that? So 8 is now in its correct position. It started in position 1, and now it's at, or in position 0 rather, and now it's at position 4. So it's now in its correct position. Okay, that's how BubbleSort gets its name. The largest item is going to bubble up to the top at each pass. Okay, so what will happen next in the next pass of BubbleSort, and we'll see through it, we're going to go through it together now, is that 4 is going to bubble up to its correct location. Which we know is just before the 8, right? That's where 4 is supposed to be. It's supposed to be just before that 8 over there. Okay, so let's see that. And it's just going to do it through a sequence of comparisons and swaps. So we're going to start. We're going to do a comparison. Okay, we're going to do a quick comparison. So the first comparison is to say, okay, is the thing on the left greater than the thing on the right? that is false, right? The thing on the left is not greater than the thing on the right. Now, that's the first time we've seen this, right? Before, always the thing on the left has been greater than the thing on the right, and then we swap them. But when the thing on the left is smaller than the thing on the right, we are not going to do anything, okay? So we just do nothing. So we did the comparison, we do nothing, we move on to the next step, okay? So we move on to the next step. Is the thing on the left greater than the thing on the right? Yes, it is, okay? So we're going to swap them. We ask the question again. Is the thing on the left greater than the thing on the right? Yes, it is. We're going to swap them, okay? We ask the question again. Is the thing on the left greater than the thing on the right? No, we can stop, okay? So that's it. That was the second pass. And what do we notice? 4 is now in its correct place, okay? 4 is now in its correct place. All right. And now you guys can see, so 3 is actually already in its correct place as well. So what's going to happen next is that 2 is going to bubble up to its correct position. Okay, and we'll see that now. So we'll say, is the thing on the left greater than the thing on the right? And remember, guys, I'm just applying the same rule every time, right? I ask the question, is the thing on the left greater than the thing on the right? Yes, it is. Okay, and we can see, so BubbleSort, the algorithm will keep going, right, until it's satisfied that the list is sorted. But you can see that that's it. Like as far as we're concerned, that's the array is sorted. Okay, so nothing else would change. Okay, and that's it. BubbleSort is done. That was a single run of the BubbleSort algorithm, and you can see that the array is sorted. But now we want to discuss, like, okay, so we can understand this maybe at a logical standpoint, right? It's fairly straightforward. You just compare. You compare. Do you need a swap? If you do, you swap. You compare. You swap if you need to. You compare. You swap if you need to, and you continue. Okay. But what we want to see is, how do we actually program this up? How do we actually program it? Okay. So let's jump in and actually do that. Okay. So I'm going to create a little like example here, and we're just going to program up the BubbleSort algorithm. Okay. And it won't take us too long. I hope we can finish before the end of the lecture. So I'm going to create a public, it's going to return a list of integers, okay, like that. We'll call it BubbleSort because it's the BubbleSort algorithm. And it's also going to take in an array of integers, okay? So I'm going to give it the array of integers, and I'm going to call it numbers. Okay, I'm going to call our array of integers numbers. In fact, actually, I'm going to call it nums just so it's slightly shorter, okay? Like so. Okay, so I've got that little method over there. Okay, and what we're going to say, so I'm going to create an array of integers. So I'm going to say int nums equals new, and I'll just create, in fact, let's do this exact one. So I'm going to say, so we're going to have 82413, okay? 82413. At the end of each step, I'm just going to go over this list of numbers. So I'm just going to, or at the end of the entire running, so I'm going to say nums equals BubbleSort nums. So I'm going to give my method, which is called BubbleSort. I'm going to give it the list of numbers that I wanted to sort. So nums, whatever nums is going to be replaced by whatever BubbleSort returns, this BubbleSort thing, and I'm going to give it the nums array. Okay. And then I'm just going to print out nums. So I'm going to say for each int num in nums, we are going to print out nums at the end, just to see whether or not our algorithm is working. Okay, so I'm going to say console.write. We'll say num plus. Well, that, I'm not sure if it'll work that way. Let me just do it the fancy way. I'll just say like, so just with this little space after it. So all this will do currently, since we haven't programmed BubbleSort at all, okay, we haven't programmed it at all it does is just return the array that you give it. This is just going to print out our initial array, okay? Unless I didn't declare things correctly. Sorry about that. Let me just fix this. So it's saying on line 15, we've got some problems. We should maybe say new. Is that how we do it? Program BubbleSort int. Oh, no, I'm being silly. Sorry about that. There you go. But an object reference is required for the non-static field of problem program bubble. Oh, right, okay, static. There we go. Okay, sorry about that, guys. And now you can see all it does is prints out 82413. So that's our simple little array there. So it just prints out 82413. That's all this does, okay? It's just a simple example. And again, you guys don't need to know this bit. The important part for us is what this BubbleSort algorithm is doing, okay? How to program up this BubbleSort algorithm. So what I propose is we do this in steps, okay? So that you can understand sort of each flow of the BubbleSort algorithm, okay? So we are given this array of integers nums, and it holds 82413. What I wanted us to do is pass over the first step. So what I want us to do is make 8 bubble up to the top. So we're going to do a comparison, a swap, a comparison, a swap, a comparison, a swap, a comparison, a swap. Okay, but I want us to do it in a way that is automatic. So I want you guys to count with me, guys. So in the chat or just by yourself. So count with me, and at the end of it, I want you guys to tell me how many comparisons we did. So remember, the blue line is a comparison. So count them with me. So we've got comparison, swap, comparison, swap, comparison, swap, comparison, swap. So that was one pass, guys. How many comparisons did I do there? We did 4 comparisons. Precisely, we did 4 comparisons. Okay, so that's a fairly good start. Now, how many numbers do I have in my array here? So Yusuf, you said 4. How many numbers do I have in my array? Also another fairly simple question, okay? Cool. So what do you think the relationship is? Like, let's say I had another number over here. Let's say we went ahead and just added like a 5 over here. How many comparisons would I now do? How many comparisons would I do? I would now do 5 comparisons, right? So I now have 6 items in my array. I would now do 5 comparisons. Let's say, what if I had yet another number? So let's say we added another number to our array. We added a 6. How many comparisons would I do now? We would do 6, right? We now have 7 items in our array, and we would do 6 comparisons. So what if we had another item now? So let's say I added now a 7. How many comparisons would I do? So we now have 1, 2, 3, 4, 5, 6, 7, 8 items in our array. We would now do 7 comparisons. So hopefully you guys notice there is a relationship, right? So let's make this dynamic, right? So I want you guys to understand the relationship, okay? Be able to create it yourself. So let's say if I have n things in my array, so the number is n. I have n things in my array. How many comparisons would I do, guys? If I have n things in my array, I don't know what the number is, but I have n things in my array. So it's a number, some number n, okay? How many comparisons would I do? And you don't have to give a specific number. You can give a number in terms of n. So how would you write what number of comparisons I would do in terms of n? It would be n what? N minus 1, exactly. We would do n minus 1 comparisons. Okay. So whatever the length of my array is, I'm going to do 1 less comparison than that. Okay. So that's fairly sensible. In fact, I know how to program this. So let's go and see if this makes sense to us. Okay. So if you guys remember, like a while back in chapter 1, we discussed this idea of a for loop, right? So for loop, we have this, okay? That little structure there, okay? What this has is that it has 3 things, right? It has the initial point where we start. It has a condition, which is where we stop, which is where we're going to stop, okay? and it has in increments, okay, which is how much we go up by each step, okay. So what we're going to do, we're going to do another little puzzle, okay. So we're going to go through the starting and ending points of each, or like the left and right of each point. So let me do it this way, okay. So on the first comparison, I'll do the first example for you guys, and then I want you guys to do it yourselves, okay. So we're going to start. The first point is to say, all right, we are comparing the thing on the left to the thing on the right. Okay, so I'm going to type out the index. We are comparing index 0 to index 1. Okay. On the next comparison, so we are comparing index 1 with index 2. Okay, and I want you guys to complete the cycle. Okay, so that was index 1 and index 2. What's next, guys? What indexes are we comparing next? Because you guys can think about, exactly, we're comparing 2 and 3, right? Because this is index 0, 1, 2, 3. And exactly, you already know, you don't even have to see the blue line. The next comparison we're doing is index 3 and 4, right? Exactly. And we would do 4, 5, but remember, we don't have 4, 5. We only do 4 comparisons. So our first comparison was 0, 1. Our second comparison was 1, 2. Our third comparison was 2, 3. And our last comparison was 3, 4. Okay. So those are the 4 comparisons that we do. Now, it's fairly cool, right? Because we're always comparing. If I is 0, right? So if we start at 0, we are comparing this item to 0 plus 1. Okay. If I is 1, then we're comparing the item to 1 plus 1. If I is 3, continuing, okay? You're always comparing it to the thing just to the right of it, okay? So it's always like this. We're going up by 1 each step, okay? You can see the thing on the left goes 0, 1, 2, 3. That's the index on the left, and the index on the right is just 1 more than that, okay? Cool, so we start counting at 0. That's the first thing that we need to see. The first comparison we do is between 0 and 1, and that will always be the case, right? That's the first comparison. You can see on the next step as well, the first comparison is comparing 0 and 1, okay? On the last step as well, the first comparison is 0 and 1. Okay, so we always start counting at 0. So let's program that up, okay? So the for loop will start at int I equals 0. Okay, int I equals 0. That's the start of our for loop. Okay. The condition, okay, when do we stop? So let's take a look at this. Okay, so we say 0. Okay, so we start at 0, 1, 2, 3. The next step would be 4, which is the number of comparisons that we do, which we've already established is always 1 less than the length of our array. So we stop we run while I is less than the length of our array. So nums.length, because remember our array is nums. So nums.length will give us the length of our array minus 1. Okay. So whatever the length of our array is, 1 less than that is how long our for loop is going to run. Okay. That's all that's saying. And you guys have already understood that relationship logically, right? We went through the steps. You guys know. It's always 1 less than the length of the array. Our length is less. Our array is length 5, so we do 4 comparisons now. If it was 6, we would do 5 comparisons. If it was 7, we would do 6 comparisons. And that's all that's saying, okay? And we go up by 1 each step, okay? So we'll say I plus plus, okay, I plus plus. And you guys remember that just adds 1 to I. We could also say I equals I plus 1 if you preferred, okay? Cool. Let me speed up a little bit. So what we're going to do next is we're going to program up that simple little rule. Okay, we're going to program up that simple rule. So actually, if I did this now, so I could show you now, console.writeLine, I could print I. Let me do it this way. So I could print like this. I could print I and I plus 1. And I want you guys to notice. So what this for loop will do currently is it's just going to print I and I plus 1. Okay, I and I plus 1. So what do you guys notice? 0, 1, 1, 2, 2, 3, 3, 4. You guys see it's going over the indexes, the exact ones we typed. 0, 1, 1, 2, 2, 3, 3, 4. Okay, so that's just I and I plus 1. Very simple, okay? So now we just need to actually do the comparison. So what we would do is we would say, if the thing on the left, so if the thing on the left, that will be nums in position 0. If the thing on the left is more than, so if nums in position I is greater than nums in position I plus 1, so if the thing on the left is greater than the thing on the right, then we're going to swap them. And how will we do that? We will save the thing on the left into a temporary variable. So I'm going to say int temp equals nums in position 0. We are going to say nums in position 0 is equal to the thing on the right. So the thing on the left equals the thing on the right. Oh, sorry. We should say nums in position I. Sorry about that, guys. That was silly of me. So if the thing on the left is greater than the thing on the right, if nums in position I is greater than the thing on the right, then we save the thing on the left into a temporary variable. We overwrite the thing on the left with the thing on the right. And then we overwrite the thing on the right with whatever's in the temporary variable. Okay. And that's it. That's that inner bit. So when I run this, I'll want you guys to notice. So I'm just going to make the code look a little bit prettier just by backspacing everything. Okay, there we go. So when I run this, I'm going to zoom out a bit. So notice initially it was 82413. Okay, 82413. When I run this now, you can see by the end of this inner for loop, you can see I end up with 24138, which is exactly what we have in the slide here, 24138. So all this did, all we programmed here is this inner step. It does the first comparison, thing on the left to thing on the right. Does that next comparison, thing on the left to thing on the right. Next comparison, thing on the left to thing on the right. Next comparison, thing to the left and thing to the right. Okay. And all we have to do now is repeat this. Okay, guys, all we do now is repeat it. Okay. So when I remember I told you guys, so you remember how BubbleSort got its name, right? So how many items, so each item bubbles up, right? Each item bubbles up to its correct place, starting with the largest item. The largest item bubbles up, okay? So 8 bubbles up, 4 bubbles up, 3 bubbles up. It was already bubbled up, but you could imagine, like, let's say 3 was at the beginning still, it would bubble up. 2 bubbles up, and 1 doesn't need to bubble up, right? Because 1 will be in its correct place automatically. So guys, I have 5 items in my array. So there are 5 things that need to bubble up, but 1 will already, the first item in the array will already have bubbled up automatically after the other n minus 1 have bubbled up already. So all we have to do now to complete the implementation of BubbleSort is to repeat the inner step n minus 1 times again. So all I would say is int j equals 0, while j is less than nums.length minus 1, j plus plus. Okay. And literally all I'm going to do is this for loop that we just wrote, all of this code over here. Okay, all of that code over there. I'm just going to put it in I'm just going to make the repeat just like, I'm just going to make it repeat again, because you can picture, so let me actually show you as well. So after the 8 bubbles up, okay, after the 8 bubbles up, so here, after the 8 is bubbled up after that first step, which is what we programmed on that inner loop, all we do is repeat the same step n minus 1 times, and the array will be sorted. We just keep repeating that same process over and over again. And so you can see now when I run this, by the end, we end up with 1, 2, 3, 4, 8. You guys see that? 1, 2, 3, 4, 8. It's sorted, just like it is in the slides. 1, 2, 3, 4, 8. Okay. And you can see if I now go ahead and add a 5, a 6, a 7, we can add an 11, a 13, a 21, a 42, 103, whatever. You can add whatever you want. As long as you make that array, doesn't matter what order it's in as well, you can see it'll always end up sorted. 1, 2, 3, 4, 5, 6, 7, 8, 11, 13, 21, 42, 103. Okay. We can make it a little bit more interesting by saying the 42 can be there, the 21 can be there, the 103 can move over there, the 13 can be over there. And you can see when we run it, it's always going to end up sorted. Okay. And that's what BubbleSort is doing. We just showed the computer how to sort a list. Okay. And that brings us to the end of the lesson. Thank you guys for coming. Thank you guys for sticking through. I think some people had power issues as well, as unfortunately. But yeah, hopefully next week when it's not a long weekend, our attendance will improve again. But yeah, thank you guys for coming. And you guys are now officially actually at the end of first year computer science, which is interesting.
Thank you, sir.
Cool. Thank you guys for coming. Enjoy your weekends, hey, and cheers.
God bless you, sir.
Yeah, you too, Chico, you too.